Hello, I'm Nick Montalbano with the Radio Navigation Laboratory at the University of Texas at Austin, and I'm here today to talk about game-theoretic counter-UAV for real-world situations. In January of 2015, an errant unmanned aerial vehicle crashed on the front lawn of the White House. A local hobbyist was playing with the drone when his remote disconnected. This activated the UAV's return to home feature, which, after a stroke of bad luck, plotted a trajectory that took it straight over the White House. It ran out of battery while it was over the White House and fell out of the sky. This triggered a lockdown and sent the Secret Service scrambling to find new technologies with which to handle unmanned aerial vehicles. Since 2015, several new technologies have emerged to handle UAVs. For example, there is the Rafael drone dome, which uses radar and visual tracking to localize a UAV. This is then followed up by jamming, and in the final stages of the interception, the device deploys laser-based countermeasures. This is practical at dealing with a single UAV, but may have unfortunate side effects when employed to defend sensitive areas like airports. For interference with friendly electronics is an undesirable side effect of any type of electronic countermeasure, which makes this device impractical in these settings. Far more promising in a general context are drone hunter drones, which track an unmanned aerial vehicle, fly to it, rendezvous with it, and capture it in a net so that it can be brought safely to the ground. We believe these to be safer and more scalable than conventional weapons like bullets and missiles, and pose less of a threat to friendly electronics than electronic weapons. However, before the UAV can deploy a net against the target, it must fly to it. Every interception begins with a game of pursuit. So what pursuit strategies are effective and practical? Well, there are simple velocity matching based techniques and a variety of heuristics that can be used here. However, they are not mindful of what is costly to you. They do not consider your own fuel usage or eventual time to intercept. We can consider our own costs by employing optimal control-based strategies like linear programming, but these require a stochastic model for the evader. They don't consider what he is likely to do or what his costs may be. Far more useful are game-theoretic pursuit-evasion and reach-avoid techniques, which consider the costs of both players. In any situation in which two players have costs, the Nash equilibrium is a valuable consideration. The Nash equilibrium is the strategy from which neither player can depart without increasing his own cost. This ensures cooperation on a pair of strategies by the two players, and also enables prediction of possible controls from the opponent. Our approach is to enumerate possible control strategies that each player may employ over some time horizon. This allows us to generate a finite global game shown here in normal form, and we can find the Nash equilibrium of this, albeit with significant computational effort. This formulation allows us to do numerous things that are difficult to do with classical formulations for differential games. One of these is cost learning. In the classical formulation for pursuit evasion games, it is assumed that all costs are known by all players, but the other guy may not be interested in telling you how much fuel he has left on board. Combining enumeration with a particle filter allows us to learn this online. We've also examined different dynamics models. In the classical formulation for pursuit evasion, all vehicles are treated as point masses, and a simpler problem is solved. However, we have found that this is inadequate for more dynamically constrained vehicles, such as quadrotors, which can have significant differences between pitch and roll authority based on their design. It is tempting to employ simpler models to solve a computationally less expensive problem. However, this may result in the opponent playing a strategy that is perceived to be Nash to him, but is not the true Nash strategy, and responding to his suboptimalities may reduce your own costs. Employing a hypothesis test allows us to pick the right controller for any situation. Finally, we've done some work on swarm control. One-on-one games are difficult to handle larger scale problems. They don't scale very well computationally. So instead of handling the game as a single one-on-one game, we handle a set of multiple one-on-one engagements between individual UAVs rather than teams of UAVs, and we solve for the best set of pairings. This provides significant computational savings. And finally, some takeaways. Counter UAV is of growing importance. As UAVs become more common, their malicious use becomes a greater public threat. Enumeration of control strategies allows us to formulate the game slightly differently, but this formulation allows us to address concerns like dynamics models that are more difficult to address using traditional frameworks. And finally, these more practical formulations permit us some modifications to address things like unknown cost functions that are difficult to handle using traditional formulations.